Okay, Lecture 4, Substances and Mixtures. Alright, there's a bunch of definitions to know, and we're just going to assume that you have learned these and use them to solve some problems here. So, how are the terms substance, element, and compound related? So, a substance is a kind of matter that cannot be separated into other kinds of matter by a physical process. So that can be either an element or a compound. So an element is one type of atom, on here, and a compound two or more types of atoms. So substance is just a way of catching both the element or the compound. Which of the following elements are which of the following are elements and which are compounds? Well, this is carbon tetrabromide. You see they have carbon and bromine. Since there's two types of elements, this is a compound. And that's a molecular compound. For oxygen, O2, that's molecular oxygen, the most common type of oxygen, what you find in the air. Even though there's a 2 here, there's just oxygen that's present, so it's the elemental form of oxygen. Sodium chloride is sodium and chlorine, two different elements, must be a compound. Just right, see there. And S8, sulfur forms an 8-membered ring normally, and so even though there's 8 sulfur atoms, it's still all sulfur, so this must be an element. And then CO, carbon monoxide, carbon, oxygen, again a molecular compound, and sodium chloride is an ionic compound. So you can hear that. That's not a soundtrack. That's the ice cream truck going by because it's June right now, currently. 3. A 28-gram sample of carbon monoxide is found to contain 12 grams of carbon and 16 grams of oxygen. What does the law of definite proportions tell us about this ratio of masses for CO? And how can we use the law of definite proportions to distinguish between carbon monoxide and carbon dioxide? Well, the law of definite proportions was discovered in about 1800. So before that, when you had carbon and oxygen, they knew that there were these elements that made up these compounds. So if they found a compound that contained carbon and oxygen, no matter what the ratio, they figured it must be the same thing. But of course, we know there's a difference between carbon monoxide and carbon dioxide. Carbon dioxide, we breathe out. It's poisonous in very high amounts, but we live with it every day. Carbon monoxide, though, is very poisonous in very small amounts. So there must be a difference. And what they determined that 28 grams, and they didn't know that there were atoms. They were, hypothesizing that there were atoms at the time, but so that's why they went by masses here. But they knew if they had a 28 gram sample of carbon monoxide, it will always have 12 grams of carbon and 16 grams of oxygen. And the reason was, and we know that now, that there's one carbon for every oxygen in CO. We don't normally put the ones there. But because the ratio of atoms doesn't change, and each atom has the same mass, carbon always has the same mass, oxygen always has the same mass, then their ratio of masses must be the same. So now the law of definite proportions allows us to determine why there are two different compounds here of carbon and oxygen. The difference here is the number of atoms that are present. It's 1-to-1 carbon oxygen, 1-to-2 carbon and oxygen for carbon dioxide. So this is 12 grams to 16 grams, and this would be 12 grams to 32 grams by mass. So if you took a sample of CO and found that it was 12 to 16 grams by ratio, then that has to be carbon monoxide. If you took a sample of carbon dioxide, and it would be 44 grams of it, and it came up to be 12 grams of carbon, 32 grams of oxygen, has to be carbon dioxide. So the law of definite proportions tells us that if we have a compound, it will always have the same ratio of masses for the elements present, and if that ratio differs, then they must be different compounds. Which of the following are heterogeneous mixtures, and which are homogeneous mixtures, and which are pure substances? So we have gold. Well, that's an element, so that must be a pure substance. We'll just write PS. Nothing else present there, it's just the element, and we said an element is a substance, so it must be the pure substance. Salt water, we're going to assume that's not ocean water, just sodium chloride dissolved in water. There is just one phase, the aqueous phase. It's mixed down to the molecular level, which means that it is a homogeneous mixture. And this is also called a solution. So you have to think about what's happening on the molecular level. Are there little islands of salt crystals floating around in the water? No. I mean, maybe when you start, but when you dissolve it, it's mixed right down to the molecular level. If you could see down to the molecular level, you'd see all these little ions separated by the water, and there wouldn't be any clumps or anything like that. Chocolate chip cookie, that's quite obviously heterogeneous mixture. Because you can see the dark chocolate chips and then the light batter. When there's color differences, have to be at least two different compounds. Actually, for a cookie, there's hundreds, perhaps even thousands of different compounds that are present. But as soon as you see two different colors in a mixture, has to be heterogeneous. It's not mixed to the molecular level. Milk. These next two I put in here because they're a little tricky. Milk is a heterogeneous mixture. Think about what's in the milk. There's water, there's oils and fats. Well, oil and fats don't mix with water. So they, if you looked under a microscope, you'd see, look at the milk under a microscope, you'd see that it has little clusters, little bubbles of oil that are floating around in the water. Well, if you can see those bubbles, then that's another phase. That's a different part of, that's something that contains something other than water that surrounds it. So if the water and what's in that bubble aren't mixed down to the molecular level, which means you wouldn't be able to see any bubbles, it must be heterogeneous. Now this is tricky because on milk you'll see that it's homogenized. So students see that homogenized, oh, milk must be a homogeneous mixture. No, it's just that the people who bring us milk don't want the fat and oil separating out when it's in the store, because then it forms that yellow layer on top. It doesn't look very appetizing. So what they do is they take milk and they put it into blenders, and they blend it so thoroughly that the fat and oil are such small droplets that it takes several days for the layer to appear. So when they say homogenized, they just mean blended. They haven't blended it down to the molecular level. So another clue that milk is heterogeneous is you can't see through it. Same with blood. Can't see through blood. Blood appears to be pretty homogeneous, but we know that if you look under a microscope again, you'll see red blood cells, white blood cells, platelets, a host of a lot of different things that are in the blood, in the water that makes up the solution of blood. And you can since you can see them, then they must not be mixed to the molecular level. And you can think a red blood cell obviously is its own little environment that is not mixed with the water. So this would be heterogeneous. Again, can't see through it, so it's not homogeneous. Carbon disulfide, that's a compound, CS2, so that would be a pure substance. And then Kool-Aid. Well, you can see through Kool-Aid, so that should be a solution, and that would be a homogeneous mixture. The sugar and the dyes are mixed, have been dissolved completely down to the molecular level, and there aren't any clusters or clumps that are present floating around in the solution. Under a microscope, if you looked at it, you would not be able to find anything. It would just be, let's say it was red, it'd be red, and you keep magnifying down, it'd just be a red background. There would never be any clumps to look at. So it is homogeneous.